Section 16.3. The speed of waves on strings. In this session, we will explore the fundamental principles governing how waves travel along a stretched string. Our discussion begins with an analysis of the motion of the string itself, specifically looking at the transverse speed and acceleration of its individual elements. We will then derive the formula for the speed of a wave on a stretched string using a mechanical approach. We will examine the specific physical factors that determine how quickly a pulse propagates, such as tension and mass density. Finally, we will apply these concepts to practical examples involving pulses on cords and cables to see how these mathematical models function in real-world scenarios. To understand wave motion, we must distinguish between the speed of the wave itself and the speed of the string elements. For a sinusoidal wave, the transverse speed of a string element is found by taking the partial derivative of the vertical displacement with respect to time, while keeping the horizontal position constant. This calculation shows that the transverse speed is equal to negative angular frequency times amplitude, multiplied by the cosine of the quantity wave number times position minus angular frequency times time. The maximum transverse speed occurs when the string element passes through its equilibrium position at vertical displacement equals 0. This maximum value is simply the product of the angular frequency and the amplitude. Just as we calculated the speed of a string element, we can determine its transverse acceleration. This is the derivative of the transverse speed with respect to time while holding the horizontal position constant. The resulting expression is negative angular frequency squared times amplitude multiplied by the sine of the quantity wave number times position minus angular frequency times time. We find that the maximum transverse acceleration is equal to the angular frequency squared times the amplitude. This peak acceleration occurs when the string element is at its maximum displacement, meaning at the very top or bottom of its motion, which corresponds to the wave peaks and troughs. We can visualize the production of a sinusoidal wave by imagining a vibrating blade at one end of a string. As the blade moves up and down, it creates a disturbance that travels along the string. The figure illustrates how a single point on the string, labeled P, oscillates in simple harmonic motion in the vertical direction as the wave passes by. While the wave moves horizontally, point P only moves up and down. The speed of the wave is determined by the relationship where velocity equals wavelength divided by the period, which is also equivalent to wavelength multiplied by the frequency. This shows how the spatial and temporal aspects of the wave are linked. A critical principle of linear mechanical waves is that the wave speed depends only on the physical properties of the medium. For a stretched string, these properties are the tension and the linear mass density, which is the mass per unit lengths. The speed of a transverse wave is mathematically defined as the square root of the tension divided by the linear mass density. An important takeaway is that this speed remains constant for a specific string under a set tension. It does not matter what shape the pulse is or what frequency is used. The medium's properties alone dictate how fast the wave moves. To derive the wave speed formula, we can change our perspective using different reference frames. In the first frame, we see a pulse moving to the right at a constant speed relative to the Earth. In the second frame, we imagine moving along with the pulse at that same speed. From this viewpoint, the pulse appears stationary, while the string moves to the left at speed v. We focus on a very small segment of the string at the top of the pulse. This small arc has a length delta s, a radius r, and it subtends a small angle. By looking at the string this way, we can apply the laws of circular motion to the moving string elements. Using our moving reference frame, we perform A. Force analysis on the small string segment. The radial force is provided by the vertical components of the tension acting on both sides. Using a small angle approximation, this force is roughly 2 times the tension times the angle theta. We also know the mass of this segment is the linear mass density times the arc length. By applying Newton's second law for centripetal acceleration, which is velocity squared divided by the radius, we can set the radial force equal to the mass times this acceleration. When we simplify the resulting equation and solve for velocity, we arrive at the result that wave speed equals the square root of tension divided by linear mass density. Let us look at a practical example. Suppose we have a string weighing 0.300 kilograms with a length of 6 meters. This string supports a hanging object with a mass of 2 kilograms. First, we find the tension by multiplying the mass of the block by the acceleration due to gravity, giving us 19.6 newtons. Next, we calculate the linear mass density by dividing the mass of the string by its length, which results in 0.0500 kilograms per meter. Finally, by taking the square root of the tension divided by the linear mass density, we find that the wave speed is 19.8 meters per second. In a more complex scenario, imagine a helicopter accelerating upward while lifting a hiker and a sling using a 15-meter cable. We are told a pulse travels the length of the cable in 0.250 seconds. From this, we calculate the wave speed as length divided by time, which is 60 meters per second. We know that the tension in the cable is the linear mass density times the square of the wave speed. By applying Newton's second law to the hiker and sling, where tension minus weight equals mass times acceleration, we can solve for the helicopter's upward acceleration. Plugging in the values for the cable mass, hiker mass, and wave speed, we find the acceleration is 3 meters per second squared. To summarize, it is vital to distinguish between the motion of the medium and the motion of the wave. The transverse speed and acceleration describe how the string elements move up and down, whereas the wave speed describes how the disturbance moves horizontally. The wave speed is determined solely by the tension and the linear mass density. We also noted that maximum transverse speed happens at the equilibrium position, while maximum acceleration occurs at the peaks and troughs. In real-world applications, factors like the physical stiffness of a cable can act as an additional restoring force, slightly increasing the actual wave speed compared to our ideal model. We conclude with 2 review questions to test your understanding. First, consider what happens if the tension in a string is quadrupled while the mass density stays the same. Based on our formula, where speed is the square root of tension over density, how would the wave speed change? Second, think about the calculus behind the motion of the string elements. Why does the maximum transverse speed occur when the displacement is 0, while the maximum transverse acceleration occurs at the maximum displacement of positive or negative amplitude? Reflecting on the relationship between the sine and cosine functions in our derivations will help clarify these physical behaviors.